Hello and welcome to part 2 of C Programming Zero to Neural Networks, a C series where we go through C programming from scratch all the way up until neural networks. Exciting stuff, eh? So in part 2, unfortunately we're going to be stuck on a lot more theory again. This is going to be a very theory heavy, just like the last episode, just like the last part. We've got to cover these preliminary things at some time. We may as well cover them when they come up. So let's do that now, today. Let's crack on. Let's do a short intro and get straight on with the video, because today we're going to be covering primitive data types for the most part. It's an important subject. This is what we make things out of. We can switch scene. Where's our scene switcher? Magic. Just change the scene like magic. Right, we've got no files. We've got a directory set up called part 2. Let's make our file called part 2. We're going to write a quick program. Part2.c. First of all, we're going to pick up where we left off. So we're going to do our hello world application once again. Include stdio.h for our, as we said last time, our standard input output of the C standard library. We want to include that in our program. You'll be glad I kept repeating myself once you get good at this. We're going to return 0 to the operating system, and we're going to throw in a printf statement called and put in that hello world. I'm just going to make sure that runs, and there we go, we've got hello world. That's where we got up to last time, which isn't very much progress in programming. If that's all we can do, we're not going to get paid millions of pounds, are we? we need to do more than that. So before we do today's video, I just want to clear up a couple of things that I probably should have mentioned in the last one. First thing is, so this is a function, main, and this whole thing has a name. And the statements included in the return, the whole thing, it's called a function definition. So we are defining a function. So it has a few key component parts. A function has a type, has a name, has open and close parentheses after the name, and it has an open curly brace, some statements, and a closing curly brace. That's called a function definition. And the second thing is, we've got a semicolon here at the end of our printf. Now we are talking about syntax and formatting, which is an important subject here in computer programming. I will show you how important it is. If I remove that semicolon, try and compile my program, it has an error and it won't compile. It's that important that this semicolon needs to be here. Same thing with this curly brace. If I get rid of that and try and compile the program, we also get an error. So we can't sort of omit certain things when we really need them. We have to follow an exacting syntax, an exacting way of writing, which is just the way it is. A computer can't be ambiguous like a human can, where you can sort of get the gist of what somebody's saying or what they mean when they give a poor explanation or something. A computer needs an exact explanation, otherwise it all goes wrong. So every statement is terminated by a semicolon, and a function definition comprises of a type, a name, open and close parentheses, and open and close curly brackets. Well, we've cleared that up. Right, now onto this video. Right, how are we going to do this? I've not really thought this through very well. So, first of all, our hello world, our print, we have this function called printf, and it's a function, it has open parentheses, closed parentheses. This is a function call as opposed to a function definition. The function is defined somewhere else. Our printf function can do more than just print out hello worlds to the screen. For a start, we can type anything into this. We can just type in some random spam keyboard, and sure enough it'll print it out. What we can also do, if we go back to hello world, we can put a \n in the middle of our hello world. What do you think that's going to do? If you already know the answer, you'll know all the excitement to come. Hello world is now split up into 2 lines, and the reason for that is \n denotes a new line character. We call this an escape sequence. An escape sequence. That's the exact name for it. It is an escape sequence. There's lots of other escape sequences. We have /t, which, can you guess what it's going to do? It's a tab character, and it will put one tab spacing in our output. So we can do that. So we can, for example, do a couple of /n's at the start and a couple of /n's at the end. And sure enough, we've now spaced out our hello world a little bit. We've given it a bit more room to breathe. Okay, and we can do something else. Let's get rid of these. We need to introduce two printf concepts in this video. We can use a %d to represent a number. So move that across a bit. Let's space this out. Everything between this starting double quote and this ending double quote is our string. It is a string. We call it a string. We call it a string for a specific reason, which I'm not going to get into right now. And the reason I'm not going to get into it right now is because this video is about something else. We've not got that far yet. Well, when we get to string handling and character arrays, we'll cover what a string is, why it's a string, and so forth. For now, just take my word for it. Anything between this double quote and this double quote is called a string. This is what's outputted. We can put in placeholders and then replace those placeholders with values. So after these double quotes, after our string, we can put more arguments in our function. And if we put a number there, we can insert that number into the string. And we can see the output, and you can obviously guess what it's going to be, hello world 42. Let's change that to the meaning of life is 42. Hitchhiker's Guide to the Galaxy. So we can replace something in our string with a value. So let's declare a value outside of our string. So we've got this int. Int main is a type of whole number type, we said on the last part, so that we can return a 0. Well, we can use ints all over our program. For example, we can do int x equals 10, for example. We could do int number equals 4. We can call these whatever we want. We can call it that if we want. We need a type and a name, and then we assign it a value. So let's make it number. Now, there's a particular way to say this statement. So it's a statement because it's terminated by a semicolon, as we mentioned earlier. There's a particular way to say this. So obviously the shorthand way is int number equals 4. But there's a more verbose, more explanatory way of explaining what we're doing. So the explanation is we declare a variable called number of type int and assign it a value of 4. That's what this statement is described as in C programming, in the C programming language. It's important to recognize that this guy here, this equal sign, is not an equal. So we're not saying number is equal to 4, it's an assignment operator. In this context, we're assigning a value of 4 to the variable number, which is of type int. So instead, well, let's make it 42. So instead of having an actual number here, we can just put our variable in that we've just made up here, and our string, our output string on our printf statement will, when it gets to this %d, replace this %d with the number, and the number's defined up here as 42. This will work exactly the same. Meaning of life is still 42. And yeah, let's clear up a few things, shall we? We've got other placeholders that we can use. %ds for numbers within a certain range, and we're about to find a lot about ranges out. We've got ZU for numbers of massive range. We've got %air, %lf. There's quite a few of these. We're just going to need %d for now, which is reasonably sized numbers. Right, and at this point we need to introduce a whole new thing. Although we have just introduced kind of new things. We've used ints before, we've used printf on the last episode. on the last part. So what we're going to introduce is the size of operator. So we need to get our head around what an int is. And one thing we can find out about an int is its size. So let's make our variable called size underscore int. So we want to figure out, we want to assign the size of an int to a variable called size underscore int. So the size of operator is literally size of, open close parentheses, and then we put in whatever we want the size of inside of it. In this case we want int. So we can change our string to just put int. It returns the size in, can you guess? Bytes. Of course it does, it's a computer. Everything's in bytes. Size int. And then we'll make sure that's on a new line, shall we? So let's run that program and see what we get. Int 4 bytes. So that's the size of an int. It's 4 bytes. So what does it mean to be of size 4 bytes? Well, we're going to find that out. What we're going to do is we're going to introduce all the primitive data types, and then we're going to discuss what it means to be 4 bytes. Exciting stuff, eh? We've got to go through all this preliminary stuff. If this doesn't seem like, 2023 computer programming where we're all making artificial intelligence and crazy games and all those kinds of things, if this seems a bit, introductory and computer sciencey, I can assure you it's very important, very fundamental, and we need to know these kinds of things. Because when we get to programming, we're going to be using this stuff all the time, and if we know exactly what it is and not just like a vague definition of what it is, that's going to really help. Hence the effort we're going through today in getting through this video, this part of our C series. I'm very much looking forward to getting on to some proper programming, but for now, we've got to do this preliminary stuff. So what other data types have we got? Well, we have another type of int. It's called a short. We can actually write it in its full name of short int, but we generally just write it as short. So we can figure out the size of a short, and then we want to be able to display that size short, we call it. Let's just do them all and then look at them all together. We can also do a long. We can do a short, so we can do a long. The names might seem obscure at first, but I can assure you they do kind of make sense, as we'll find out by the end of this this part. We have a float. We have a double. And we even have a long double. And finally, we've got one more. We have a car. Size car. Some people call this a char. I use the two terms interchangeably. You can take your pick, whichever you feel comfortable with. It's an abbreviation of the word character, which has a silent H. So I tend to call it a car because in character the H is silent. But then if I'm using functions, there's some functions called put char and get char, and I use char when I describe those functions. So I kind of use them as and when I feel like. It doesn't really matter, as long as, well, I was about to say as long as you're consistent, and I'm clearly not consistent because I changed the names, but we're not going to get them mixed up with an int, a short, a long, a float, a double, or a long double. So car, char, take your pick. So let's print out our car as the first one. Short, so we're going to need a long. Not the most fascinating of programming stuff, this, is it? We're going to need to do our float double and long double. Float double, long double. Double, and float. Inch short, long, float. I've spelt double wrong there. Dobule. That's looking good. Right, let's print that out. Let's see what's going on with this program. There are all the different sizes. It doesn't look very well formatted, does it? Well, allow me to introduce you to something that every single computer programmer in the world loves doing. Formatting output to look nice. Everyone likes doing that, don't they? Let's line up by bytes. So the what we're actually looking for is the bytes, the %d. So we're going to line them all up. That'll do us. I'm going to put a space there. That looks a little bit better, doesn't it? I don't like that the 16 is kind of shifted over on. I can fix that, but it does mean introducing yet another new thing, so we can specify sort of minimum spacing for like padding. For our, oh, we'll worry about that another time. We'll bring it up when we can do it, but that should at least, yeah. So the 16 is lined up properly as we'd expect it to be, like right justified style. So a car is 1 byte, an int is 4 bytes, short is 2 bytes. We're going to want to put our short above an int, so they're in ascending order, aren't we? A car is 1 byte, a short is 2 bytes, an int is 4 bytes, a long is 8 bytes. A float is 4 bytes, I've spelt dobule there again, I've done it again, haven't I? A double, or a dobule, is 8 bytes, and a long double is 16 bytes. Let's fix that dobule. And let's put some headings in. So we can group these primitive data types into categories. So these are characters. New line that as well, don't we? Sketchy typing today and lots of moving around with my arrow keys. These are whole numbers, nimbus. And these are fractional numbers. I reckon let's throw some new lines in there as well, just to space things out a bit. Perfect. Right. So we have 3 categories of primitive data types: characters, whole numbers, and fractional numbers. And they are a range of sizes. A character is always 1 byte. For whole numbers, we have short, int, and long, which are 2 bytes, 4 bytes, and 8 bytes. And for fractional numbers, we have similar size range, but 4 bytes, 8 bytes, and 16 bytes, strangely enough, because we have some special circuitry to deal with long doubles. So, first of all, the obvious question that springs to mind is, what is a byte? So we're going to have to go through binary. Great. Aren't we all looking forward to this? So what is a byte? Well, binary is base 2, is a base 2 counting system. We count, those humans, those glorious humans, we count in base 10 naturally. So let's do base 10 first, because that's the one we know. Base 10. So let's say we've got the number 301. And we did some headers to sort of break our number up a bit. We did a ones column and a tens column and a 100s column. Let's say we did that with our decimal number. We know what 301 is. It's 301, isn't it? It doesn't need any conversion. But we can kind of go around the slow way of working it out, and we could do that. We've got 3 times 100 plus 0 times 10 plus 1 times 1 equals 301. And I know that's ridiculous going through it because we can see it's 301. We know we've just got back to the same 301. But the point is we can sort of column up. I've not done this very straight. It's a bit angled, isn't it? The point is these headers kind of make sense. We have a ones column, a tens column, and a hundreds column. That makes sense, doesn't it? It makes intuitive sense. So we can use that same thinking when dealing with binary. Why is this not going back? There we go. Must have had it not selected. So what have we got? We've got base 2. Now base 2 differs from base 10 in that base 10 we've got 10 unique symbols. We have 1, 0, 1, 2, 3. You know, you get the idea. I'll do them all now. 6, 7, 8, and 9. We have 10 unique symbols. Well, we don't have 10 unique symbols for binary because we were on base 2. Because it's base 10, 10 unique symbols. Base 2, 2 unique symbols. 0 and 1. Binary, 0 and 1. Let's pick a number. Let's do the same thing again. Let's say we want to find the value of 101 in normal base 10 decimal. Well, we can do the same thing again. And we can just put headers on our number. And once again we have ones. But before we jump to tens and then hundreds, because we're only in base 2 and we've got 2 unique symbols, we can only go up by a factor of 2 for each column. So we've got ones, this column is 2s. That means that this column is, if I can write, is 4s. So what does our number equal? Well, we've got 4 ones, 0 2s, 1 4s, 0 2s, and 1 1s. That equals 5. Easy. Binary is not very difficult to work out. It's just not intuitive. What about the number 1 1 1? We've got 1 4, 1 2, and 1 1. So that's going to be 7. 4 plus 2 is 6 plus 1 is 7. Easy, easy, easy peasy. Let's go back now. There's your basic binary. So what have we got? We've got a car is 1 byte. Well, what's a byte? A byte is 8 bits. And what's a bit? A bit is one of our columns in our number. So 1, 2, 3, 4, 5, 6, 7, 8. Let's try and draw a line across. Downward lines are notoriously difficult with these drawing path things. Let's do it though. Not going so. That wasn't great. I'm sure this is fascinating stuff to watch. Right, and then once again we've got 1s, 2s, 4s, but now we need to go a bit higher, 8s, 16s, 32s, 64s, and 1, 2, 8s. So that's a byte, 1 bit. That's what it looks like. And obviously 0, 0, 0, 0, 0, 0, 0 once again equals 0. So what does, if we set all these to 1, what number does that come to? Well, it's 128. Well, 128 plus 164 plus 132, so we basically add them all up together, and that comes to 2, 5, 5. So our range of values we can store in an 8-bit byte, in 1 byte, equals 2, 5, 6, because we include the 0. So we can hold 0 to 255, so total possible values of 256. Now we are at this point going to have to bring in yet another new concepts. The concept of signless. Let's jump back over to our program. Go down to a bit of empty space. So we can do int x equals 10, for for example. Now we can put a qualifier on this int. There's different types of ints or shorts. Well, we're dealing with car at the moment, but let's just do int. We can do the default type is a signed int. So we can hold -3, -32, -12, -144. We can hold negative values. We can also do an unsigned int. So there's no sign at all. There can't be a plus or a negative at the start of the number, which means we can go from 0 to whatever number, as long as it's positive. We can't do -12 with an unsigned int. So there's two ways of representing a number, and we're about to find out why. So our 8 bits has a range of 2, 5, 6. We can the computer can represent that range as either 0, 2, 2, 5, 5. Make sure that definitely looks like an arrow. Or it can represent it as -1, 2, 8 to +1, 2, 7. If it's signed, it'll be -128 to +127. If it's unsigned, it'll be 0 to 255. Obviously, with the unsigned, we can hold a bigger maximum value, but we don't have access to any negative values. The range is the same because the number of combinations with our 8 bits of 1s and 0s is 255. There's a maximum amount of combinations, values that we can hold. So that gives us an insight into what a car is. Is 1 byte. So whatever it is, it's got a maximum possible range of values of 255. Now, as I said, it's characters. Cars represent characters. Now, the computer itself doesn't know what a character is. It only knows bits and bytes. So this video is not going to be about this, because we're going to save it for another time, but just so we know how it does that, we have such a thing called an ASCII table. Now, I tried clicking on this one before when I was thinking about doing this, and all kinds of pop-ups and nonsense popped up. Websites are absolutely horrendous half the time now, aren't they? Back in the 90s and the early 2000s internet, if you wanted an ASCII table, you type in ASCII table, press the first thing that comes up on whichever search engine you use, and you would have an ASCII table right in front of you. Not the case anymore. Too many people trying to sell you things. So there's millions and millions of ASCII tables on the internet now, and half of them are sort of like trying to get you to buy things, I would guess. I'm not anti-capitalist or anything, but I do find it very frustrating. That one looks like a reasonable one. So we have to get around it by just opening the image and not actually going to the site and using Google Images. For your future reference, that's how we get around the incessant pop-ups and things. Anyway, this is not going to be a rant about the internet. This is about ASCII tables. So, you probably can't see my cursor very well. Starting up there, I'm going down to A, capital A, has a decimal value of 65. So the number 65 as a car is represented as a character A. So the computer only knows these values. But by convention, once again by convention, we by a standard, the S in ASCII stands for standards. Different numbers represent different characters. So it's just like a lookup table, like a key code. But you will notice down here, if you go to the very last value, which is blank, but I think it's actually the delete character, has a decimal value of 127. So a car in its natural state is a signed 1 byte value, which is represented as a character. I won't say any more about it than that because we're going to do string handling, we're going to do character arrays. I've already mentioned this in a more appropriate part. This part's about primitives. What time are we on? Have we massively run over? I'm trying to keep these things a bit shorter. We have massively run over. I was going to try and keep this to about 20 minutes, and I think we're already on half an hour. Right, so let's quickly do a short, and then we'll just look up the others. So, what's a short int? So if we look at our program, short int is 2 bytes. 2 bytes. So and it's part of the whole numbers. So we can have. So we're just talking about numbers. There's no ASCII tables converting numbers to characters. We're just dealing with the numbers. So let's do a short 1, 2, 3, 4, 5, 6, 7, 8. Let's do a dotted line to separate our bytes. 5, 6, 7, 8. So now we've got this many to deal with. So remember when we had 1 byte, we had a maximum range of 256. So what's going to be our maximum range for this, for a short int? Let's figure it out. So we need to do the headers again. So we've got 1s, 2s, 4s, 8s, 16s, 32s, 64s, and 1, 2, 8s. We're going to get to a big number, aren't we? So we carry on in the same way. 2, 5, 6, 5, 1, 2, 1, 0, 2, 4, 2, 0, 4, 8, 4, 0, 9, 6, getting pretty big, 8, 1, 9, 2, 16, 3, 8, 4, 32,768, I think. You might have to check those last two. Although, you spend enough time with computers, you do get pretty good at doubling numbers. Right, so obviously 0, 0, 0, 0, 0, 0 is equal to 0. What's 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. What's that equal to? We're never going to fit it in there, are we? What's that equal to? Well, it's around 65,000. We look up the actual number on Google. Short int range. Let's do int 2 byte range. That'll give us it. 2 byte minus, let's zoom in, minus 32,000 plus 32,000, or 0 to 65,000. So just like before, we had a two ways of representing signed and unsigned. So for unsigned, 0 to 65,000, or minus 32,000 to plus 32,000. That's quite a step up, isn't it? That's quite a jump in number sizes that we can deal with. And for those of you old enough to remember, home computing started on 8 bits. 8-bit home computers. So I think 286s and 8086 architecture were all 8 bits, and ZX Spectrums and Commodore 64s 8 bits. Then we had a big leap to 16-bit computers. Consoles were like the Sega Mega Drive and the Super Nintendo. And it was a big leap. Suddenly everything got a lot better, because we went from having maximum of 256 as a range for anything to having 65,000 for a range for anything. Everything representing colours. You got 65,000 colours now. You've got 16-bit because you've got 65,000 possible values to represent things. It was a big leap going from 8-bit to 16-bit computing, and you can see in numbers how that would have opened up a lot of computing. Only been able to count to 256, very limiting. So a short int is a 2-byte whole number which has these ranges: 32,768 to 32,767, or 0 to 65,535. So what about an int, which is 4 bytes? We won't bother doing the explanation. Minus 2.1 billion to plus 2.1 billion. So 4 bytes, or 32 bits. 32, so if we go to 32-bit computing, I think 486 probably a 32-bit computer. We can hold values between minus 2.1 billion to plus 2.1 billion, or 4.2 billion. 0 to 4.2 billion. There's a massive range of values. Then we've got a long int and an 8-byte range. Right, defaulted to 8-bit. Int 64-bit range. That'll tell us the right number. There it is. Look at that number there. It's massive. 5,000, that's thousands, that's millions, that's trillions, billions, sorry. Start again. Thousands, millions, billions, trillions, whatever comes after trillions, whatever comes after that. That's a big number. A long integer, an 8-byte number can have a range of -9, whatever they are, to +9, whatever they are, or even bigger, 0 to, well, 18 of them. Basically, a massive, massive number that you wouldn't know what to work with. And this kind of explains something. This explains why we're not that bothered about 128-bit computers, because we don't even really know what to do with numbers that big. Yeah, I'm sure there are things when it comes to like scientific modelling where you're dealing with big numbers. So cosmology, for example, you've got things that are really far away and angles that need to be really precise and that kind of measurements of that kind of accuracy. But outside of physics, when you're just building applications or dealing with graphics, you're not going to have a screen with that many pixels. You're not going to need that many colours. You're not going to need to represent. It's not an easy thing to find a use case for such a big number. But just for completion of explanation, what's a 128-bit range? Look at that for a number. We're going to have to zoom out to see it. There. If we went to 128-bit computers, we would be able to hold numbers of that size, which would be, well, I don't think it would make the news that we can suddenly hold numbers of that size. It would be, instead we focus now on our increasing computer speed, performance by parallelism and all that kind of thing. We've got enough bitage. It's referred to as our word size, our the 16-bit, 32-bit, 64-bit computer. That's referred to as the word size, which is what it means is we have electronic circuitry to deal with values that size, up to that size. So a 64-bit computer can deal with values up to 64 bits long, numbers held in up to 64 bits. Like a 32-bit computer can't work with a 64-bit value because its word size is too small. And then fractional numbers, I'm not going to do the same kind of explanation for fractional numbers. We kind of get the point for what we're doing here. We're working out ranges. We're finding out something about these primitive data types. The fractional numbers, 0.12, 1.546, you get the idea of a fractional number. It works exactly the same way, but to explain it is a bit more mathematical. It involves a bit more maths kind of words, and there's not a huge amount of maths in normal computer programming. It gets a bit mathsy when we get to neural networks, but most computer programming is mostly counting, so it's like do that thing for that many times. The explanation of how fractional numbers work in a computer, I mean, maybe it were worthwhile doing something on that at some point, but at this stage we can just think of it works exactly the same way as the whole numbers, except it's split up. So there's a few of our bits to hold a bit before the decimal point, and then the rest of the bits are to hold the thing after the decimal point. So we can have like 124.546000012. And there's some space at the start to store the first bit, which is a limited range, and there's some space at the stuff at the end, at the part at the end to hold the values of after the decimal point. Not the best explanation, but it's enough to get an overview. So a floating point number, it's called a float because it's a floating point number. The decimal point isn't at the end, it's somewhere in the number. The full explanation involves a mantissa and an exponent, and we don't want to use that kind of language yet, we just want to stick to programming terms. A double is called a double because it's a double precision floating point number. It has twice as much space after the decimal point in which to hold values. Now, you might wonder why that's important. Well, if you think of angles, if you've got a really precise angle, you need lots of decimal places. An angle isn't just like 25 degrees and then you jump up to 26 degrees. If you're quite a long way, you've moved a big distance. So going back to cosmology and astronomy, we need really precise angles to measure where things are. But also for things like games and 3D graphics, from what we're working out there, polygons in 3D space, angles, lots of angles. So we have a float, which is a standard precision floating point number, a double precision floating point number, which has twice as much precision accuracy for any kind of angles that we might want to represent, and a long double, which is 16 bytes, which is a quadruple precision floating point number, and there's some special circuitry in the CPU to handle that. Even though we don't have a 128-bit computer, we can work with long doubles. I don't think the process is entirely atomic. That would take too much of an explanation, but basically I don't think it's very computationally efficient to work with long doubles. I think it takes more than one tick to work, to clock tick to work with them. We'll be mostly working with floats when we get to neural networks. Floats is enough precision for us on our neural networks. But the important thing is we know the three categories of primitive data types. We have one called a CHAR, which is 1 byte and holds numbers which represent characters in an ASCII table, and that has a maximum possible range of 256. We have whole numbers of short, int and long, where we have a short is minus 32,000 to plus 32,000, an int is minus 2.1 billion to plus 2.1 billion, and a long is minus massive number to plus massive number. And then fractional numbers work exactly the same way, only the number of bytes denotes the amount of precision we have on our fractional number, how much precision. Like obviously 0.00000000000000000000001 is very precise number. We might need a double to hold that number in, but 0.52 would go fine in a float because we don't need that amount of precision. We've only got 2 decimal places. So that about does it for this explanation. I was going to tag something on the end of it, but we're at 40 minutes now. That's far too long, so I'm going to have to speed up these explanations somehow. But this is preliminary stuff. I guess it's worthwhile. I mean, I've got no subscribers or anything at the moment. I guess it's worthwhile going through this. So in the future, if anyone gets hooked on my neural network series, when we get well into it and they want to go back to the start, we've explained everything all the way up to our neural networks, which is kind of the point of the series. And this is its raison d'etre, its reason for being. We'll call it a day at that because it's been such a long video. I won't do a big outro. Right, I will see you next time, and hopefully on to slightly more applied programming kind of topics. We'll see. See you next time.